Hello everyone, I'm Jiang Ling from Moldex3D. Welcome to today's webinar, and we're going to talk about what is a new function in R17. I'm not going to just tell you what is the new function. I will also show you how to find those icons to use this new function. Okay, first we are happy to announce that the Studio now is our standard platform now, due to some enhancement of the Studio usability. In the past, some of the function were missing in Studio, so we've been forced to use the old interface in some case. But now we already put most of the function in Studio, so we can just use this one as our standard platform. And as you might note, that in Studio we can do almost everything in just one interface, including import a geometry, create a mesh, select material, set up others inputs, run the simulation, check the result, and also generate the report. And in R16, the Studio only support injection molding, and now in R17 we support most of our advanced process like powder injection, injection compression, gas assisted injection, foaming process, and cold injection and bi-injections. And how to open those advanced process? Let's see a demo. First, of course, we need to create a folder to save all the data. And then in here, the molding type, we can select what is the molding type we're going to use for the simulations. For example, I select the injection compression molding. Okay. And then we can keep import geometry, set up all the inputs, and run a simulation. And the idea in the Studio is quite simple. We always go from the left to the right, and we are able to complete the simulations. So first we create a new run, set up the molding type, import the geometry, create a mesh, set up material, set up the process, analysis secrecy, and computation parameter setting, run a simulation, check the result, generate a report if you want to use it. And some of our users will ask if they have an old project, they have an old simulation result done by the old interface, how we can open and check the result in Studio interface. First, we open the folders done by the old project, and we are able to find one file name called M3D file. This is a project file, which is the old interface. If we double click, it will open with the old interface. So if we want to open it with Studio, we can just drag this M3D file into the Studio interface. And the Studio will convert all the data to the new file format for Studio. And we can just view the result now in the new interface. And if we open the folder again, and we can find there's a new file created by the Studio called MRM file. So once we open the M3D file with Studio, this MRM file will be created automatically. And next time we can just double click on this MRM file to open it with the Studio interface. The next function I would like to introduce is our distribution curve and history curve functions. And since we have the other powerful function we can find in the R16 Studios called prop. It's kind of like the old function in project, like the major nodes, but this prop function is more efficiency. And with this prop function, and we can just extract what is the history curve at specific nodes, or the distribution curve along the specific directions. Let's see how to use it. First one, how to extract the data along the thickness directions. Okay, as I was saying before, first we need to have a prop. So I just use prop and just put 2 nodes on the part. And in this display settings, we can set up if we want to show the name of the prop. And also, if we are going to show the value of the prop, if we show the value of prop, we are able to see what is the temperature at the location of prop 1, what is the pressure at the location of prop 1 or 2. And once we have a prop, then we can go back to use the thickness function here. And we are able to select what is the time step we're going to draw the thickness data, like the time step of end of feeding or end of packing or end of cooling, and what is the result, maybe is temperature along the thickness direction or fiber orientation along the thickness direction. Now I want to show the fiber orientation at end of feeding. So I select the end of feeding, fiber orientation of X, and at location of prop 1. So you can see this is the picture. This is a curve of the fiber orientation in thickness direction. Okay, now the other one is the Y fiber orientation in Y directions. We're also able to export this data as a CSV file. Let's go back to the thickness. And in here, we have a small icon writing CSV. You just click it, and we are able to export the CSV file. Okay. And the next functions is the history curve. Let's see how to use it. First, also we need a prop too. For example, I want to know what is a shear rate at the gate regions. So first, I will put the prop close to the gate. So use clipping and prop function together, we are able to put a node inside a runner or cavity. And then click the history. Okay. Before select the prop in here, we are able to draw the general history curve like sprue pressure, clamping force, flow rate, and others. And if we have a prop, we can just select the data as an all prop, and then we can check what is the node we want to draw the history curve data, and also select the result. And in this case, I will draw the history curve data of shear rate. Okay, it's quite high all the time. So generally, the polymer can only handle like lower than 8,000 or 6,000 shear rate. And in this case, it's too high during the feeding time, so the material might be damaged. So increase the gate diameter or slow down the feeding time might help. And let's see what is the next samples. Let's say I want to know what is the temperature data, temperature history curve at the other node. I will switch to the packing result temperature and put another prop inside the cavity. So it's prop 2. Click the history curve again. And this time I will select the prop 2 and see what is the temperature result at prop 2. Okay. By the way, for the history curve data, it is possible to export a CSV file as the thickness data. So we also have a CSV icon here. Just click this one, we are able to export the CSV data. Okay, and this one is the temperature result at prop 2 from the feeding to the end of cooling. We can know when this position will reach the frozen temperature and ejection temperatures. And you can see this curve is quite smooth because I have 30 output in the feeding stage and also 20 output in packing and another 20 output in the cooling. So this curve will be quite smooth, but in the default setting, the output in packing and cooling only have there's only 3 outputs. So I recommend to increase them before we run the simulation, because if we have only have a 3 output or 5 outputs, the curve can only draw by 3 or 5 points, then the resolution is not good enough. So in the computation parameters, we can set up how many output we want for the feeding, packing, and also including we can set up the output number. Okay, and the next one is distribution curve, and we can put a lot of prop and see, for example, what's the pressure loss in the thickness. Sorry, the pressure loss along the specific directions. So first I will put the prop along X direction. And then to use the distribution function, first we need to group all the prop as a group. So now this one is a group 1. And then we are able to use the distribution curve plotting functions. Click the distribution curve icon and select the group number, and this one is group 1. And I want to know what is the pressure lost in the feeding stage along the X direction. Okay. So you can see here This is the first prop very close to the sprue, and this is the last prop very close to the end of field, the last field regions. So you can see how the pressure drop along the x directions. And the other sample, we can also use this distribution curve to draw something like flatness. So first I will put the prop along to the edge of this plate. I will speed up a little bit. And first I have a lot of a prop. I need to group them together. And this time is group 2. So we can check what is the Z displacement. And it's kind of like flatness. If we put all of the prop along the feature line, so we can know what is the kind of like flatness. Also, it's possible to export the CSV file. Also, click this icon. Okay, next one, we have some improvement for our color bar. Just directly see the demo. Now it's possible to move the color bar. We can decide if we want to put on the left or right. And also if we want to show the banded distribution. Inverse the color bar. And also double click, we can change the maximum value of the color bar or the minimum value of the color bar. Double click, we can just input the number. For example, I want to show where is the shear rate higher than 6,000. I just input 6,000. And rest of them I use fill out of regions. So you can see here, the red color means this region have the value higher than 6,000. So it might cause the problem. The material might cause, the shear rate might cause some problem to the material. Also, we can use this one to find a hot spot or high variable shrinkage regions. And the other one is fix the minima and maxima region while we switch the time step. It's quite useful. For example, we want to see how the part cool down. Like now the time step is 0.3 seconds. I want to see how the part cool down just by the color of this result. But once we switch to the next time step, you can see the minima and maxima number changed. So it's very difficult to see anything just from these colors. But once we use this fixed range, and we switch the time step, the range won't change anymore. So we can just see how the part cool down just by the color. And also it works when we check the temperature of the mold base, or see how the pressure transfer from the runner to the cavity in each time step. And next function is roundness. So we are able to directly see what is the roundness in our studio interface, or export the CSV file with this radar picture. Okay, let's see how to use it. To use the roundness, first we need to have a Wabbit result, and we must select the displacement result. Otherwise, the roundness function will be grayed out. We are not able to click it. So click the roundness and select where is the measurement position. Just click the edge, and the program will automatically express the selections. And save and close. You can see what is the radius of the least square circle, and also what is the maxima radius, the minima radius of this circle. Also the roundness. Let's see one more time. Click the roundness, select the measurement position, save and close. We can see what is the roundness at this position. And to export this data as a CSV file, we need to switch to the attribute tree and select the roundness. It depends which one we want to export. Select the one of them. For example, I select the roundness 1 and right click. We can export the data as an Excel file or CSV file. And if we want to remove them, also select them, just click delete. We can remove this measurement data. Okay, this is the CSV file of the roundness. We can see what is the coordinate before the deformation, after the deformations, and all the other detailed data. Yeah, and also this radar pictures. Okay, let's see the next function. It's to export the warpage result. We are able to view what is the shrinkage and change the scale to understand what is the warpage tendency, if there's a bending problems, and find out what is appropriate mode compensation value, and also export the model with shrinkage or with opposite shrinkage, or with the original model with mode compensations. So we don't need the CAD file to do the mode compensation. We can just do the mode compensation in our interface and read the export ST file again, generate the mesh, rerun the simulation, and check if the final dimension fit to our target dimension. And let's see how to use it. First, of course, we need to have the warpage result, and click deformation. And in this scale factor, we can just change it to see what is the warpage tendency. If it's a scale 1, it means it represents what is the final shape of this model after shrinkage. And this black line is the feature line before the shrinkage. So the difference between two of the model is the shrinkage of this model. And it depends if we can allow this kind of shrinkage value 0.5, 0.7, 0.5, 0.6 millimeter. And to find the appropriate mode compensation value, we can just import. We can keep the scale as 1 and import the mode compensation value. For example, 2%. Sorry, 2%. And now I select the isotropic method. So when I input 2% for X, automatically the program will set up the Y and Z with 2% mode compensations. And you can see now there's no gap between two of the models, which means the the warpage is very, very small if we use 2% as a mole compensations, only 0.07 millimeters. If we change it to 1%, and we can see here, you can see there's a gap. So it doesn't, if the black line is our target dimensions, then it doesn't fit to the target dimensions. So 2% would be better for this case. And also, it is possible to use an isotropic method. If it's an isotropic method, we can set up different mole compensation value for each directions. Okay, and the next one be how to export the deformed models. You can use this icon to export the model. Okay, and here, if we select the first option, we want to export the deformed model with scale 1. So we export the model with warpage result. But if we use deformed model with a scale -1, it means we export the original model plus the reverse displacement, which the part will be bigger than our target dimensions. And we expect after shrinkage, it will fit to our target dimension. This could be one of the options to do the mole compensation. Just export the opposite warpage result. So we export the deformed model plus scale factor -1. This is one of the options for the mole compensation. And the other one is we export the model with the mole compensation values. So we export the original file size and scale it a little bit with this percentage. We was in this case we scale the part 2% bigger in X and Z direction and 1.5% bigger in Y directions. Because we already check in our warpage result, this should be an appropriate mole compensation value. And we can just let's set up the file name, location, and start export the STL file. And we can use the export model to run the simulation again. And please remember that always run the second one. Don't just use this mole compensation result and do the toolings. Please run another simulations, because when we change the dimension, it might change the other data too. It's not guaranteed that with this value, the part will always shrink to the target dimension. Please always run a second one to confirm that with this kind of mole compensation, the model after shrinkage will fit to the target dimension. Okay. And the next part, I want to introduce some of the useful functions for the pre-processing. Okay, first one is our enhancement of cooling channel wizard. In the past, we have a template for the cooling channel, but it's very difficult to use because we only can see this is template 1, template 2, template 3, and we don't know what it looks like. just name of template 1, 2, 3, 4, 5. It's very difficult to know which one I want to use. And so in R17, we have a picture to represent different type of cooling template. We can select which one we want to use and set up the dimension. Okay, let's see a demo. Okay. First, click the cooling channel, and we have the option template. And we can select the template we want to use. And we can set up what is the directions. At the very beginning is in X directions. We can switch to the Y direction. And also we can decide if we only want to put the cooling channel in one side of the mold or both sides of the mold. And input the dimension for each section of cooling channel. I want to both sides have a same cooling channel. And then we are ready to go to the next step, set up the inlet, outlet for the cooling channel, create a mold base, doing the mesh, and rest of them. Okay, so I'm gonna go to the next function. And in each version, we put a lot of effort in the meshing to improve the meshing kernel. And you can see that in this version, we are able to set up different corner for the hot runner or cold runner, and some special settings like this kind of mill flipper design runner. And also if the cooling channel are not, the central line of cooling channel not touched to the other one, we still can generate the cooling channel mesh. But to use all these mesh functions, we have to enable this one, generate HESA-based solid mesh. We can find it in the preference settings. Without this one, we are not able to use those new mesh functions. And let's see how to set up the preference. This is a simple hot runner. We are not able to set up the different type of corner because the option is disabled right now. There's nothing we can change here. So we go to the preference here and go to the meshing control, solid. And here we can find the option generate HESA based solid mesh. Check this one and go back to the studio. We can find out that the corner is different now. And we double click, we can change the different type of corner for the hot runner or cold runner. Okay, it's the same for this kind of cold runner too. If we don't enable the general HESA based options, and it's not able to generate this kind of runner layout, it will show this error message. We cannot, it's not support, we cannot, the program cannot generate a solid mesh. So we go to the reference setting, enable the HESA based runner option, and we are able to generate a solid mesh for this kind of runner layout. Okay, see, there's no problem for this kind of runner layout. Let's see the next one. get review, some improvement for the get review functions. In the past, if we have a part and part insert, and if the gate is very close to the part insert, after the gate reviewed, it will change the mesh in the contact surface, in between the contact surface, and it causes the non-matching problems, and it's very annoying. So now we have these options. Once we enable these options, the matching surface mesh will be fixed. It won't change anymore, even the program doing the get rebuild. Okay, let's see a video. This is a part with a mold insert, and it's already matched. You can see this blue color means matched mesh. And generate, you can see this already matched. And generate a solid mesh. You will show the error message due to the non-matching problem, but it's weird because now it doesn't have any non-matching issues. But after get review, there's non-matching issue. And once you delete solid mesh, non-match problem just gone. So it's very difficult to fix it in the previous versions. You see here, after the get review, there's non-match section on top of mold insert or in the bottom of cavity. You can see this mesh is different because the get rebuilt. So also go to the preference settings, mesh control, solid. There's option called keep mesh face during the get review, and then generate the mesh again. And you can see that in this time there's no error message. And if we checked the mesh size on the contact surface, you can see the mesh is the same. It doesn't change due to the get review process. So if there's a insert and the get very close to the insert, please enable this option to avoid the non-matching problem. And next one, we have some improvement for the no seeding. And let's just see the example, easier to understand. This is also, it's almost the same simple. I have a geometry runner, and I have a part, I have an insert, and in the past, sometimes there's a simulation problem because the resolution of the gate is too low, or the resolution at sprue is too low, because we give the wrong mesh size. So personally, I recommend to do the no seeding separately. First, we do the no seeding for the runner. For the runner only, because this mesh size, this default value for the mesh size have some meanings. It represents twice of the thickness of this part. So if we select everything together, and we don't know how to decide the mesh size. For example, I select the part and part insert together. Oh, sorry. If we select the part and mold insert together, and the mold insert have a very big thickness, and we don't know how to decide the mesh size. But if we do them separately, I can understand. I can easily give the appropriate mesh size. And the improvement in R17 is that there's an auto refine for the runner. If it's a geometric runner, you can see here. In the sprue regions, it's automatically refined. And also at the gate regions, the mesh is very dense. And do the node seeding for the part. For example, I see when I do the node seeding for the part, I see this one is almost 6. It means the average thickness of this part is 3 millimeters. And I will use 3 millimeter for this part. And then do the node seeding for the insert, for the mold insert. Now you can see the default mesh size is 130. If I do the node seeding with a part together, it's very difficult to know what is the average thickness for the part, for the mold. So sorry, for the part, for the mold insert, or for the runners. And in this case, I will just use 10 for the mold insert. Okay, here you can see once I do the node seeding as 10, all the edge we have the mesh size as 10, but the contact surface with a part is automatically refined because I already finished the node seeding for the part. The program will automatically copy the mesh size to the insert. So I recommend to do the node seeding for the part first and then do the node seeding for the insert later. So the insert can copy the appropriate mesh size from the part. And it would be better when we do the matching mesh because it will be easier for the program to do the automatic matching process. And also it will be better for the non-matching mesh. Because if we use non-matching technologies, the mesh size should be similar in between the contact surface. So please do the node seeding for the cavity first and do the node seeding for the insert later. Okay, then next new function is modify the thickness. Let's just directly see how to do it in Studio. This is a simple case. I have a uniform thickness of each rib. So we have when we go to the once we generate the mesh, surface mesh, we can click this one, fix mesh, and we can go to this page, this fix mesh page. And in here, we can find an icon named modify thickness. And we can select the surface we want to move to change the thickness. I select the surface and select the start point and input the distance. I want to move this surface 0.5 millimeters, and I need to give a reference point so the program will know which direction is the moving directions. Okay, so this rib will be 0.5 millimeter thinner. And right click. So you can see the thickness is smaller now. One more time. Select the surface we want to move and give the start point input the moving distance. And give the second point as a reference point so the program knows how to move the surface. Okay, this is our function modifier thickness. So we, if this is simple geometry, we can just use this one to modify the thickness. And for the solver improvement, we have 4 different improvement. The first one is that we have extra data to help us to find out the mold temperature controller. For example, if we run the cooling analysis with a 3D CFD result, and it will create a CSV file, record all the data. For example, what is the pressure drop? In this case, we said that the pressure drop in the mold base is 3 bar, and the program will calculate what is the flow rate if the pressure drop is 3 bar. And the flow rate, of course, is very high in this case. And for sure, we can reduce this pressure loss to get a reasonable flow rate in the cooling channel. Or if we have to choose the machine for this kind of the result, so we need to find a machine can at least can provide 3 bar pressure and flow rate required 280 liter per minute. If it's not, if the machine cannot provide enough flow rate, we might need to more controller. And let's see how to use it. To use this one, we must go to computation parameter. Before the simulation, we need to enable this option, cooling channel analysis. First, we need to enable this one and run the cooling simulation, and then we can find the extra CSV file in our folder. I will speed up a little bit. We can click this one, File Explorer, and go to the Analysis folder, and to find one CSV file. Then mold temperature required. Okay, for example, in this one, I use flow rate control. So it shows what is the flow rate required is roughly 15 liter per minute. But there's a problem here. You can see the pressure loss is quite different between channel 1 and 2 and 3. 1 and 2 might be, 2 and 3 might be similar, but the channel 1 have a huge pressure loss. So if we use one mold temperature controller, you can imagine that the flow rate won't be 80 in channel 1 because the pressure loss is too high. So either we use just 2 mold temperature controller, one for channel 1 and the other one for channel 2 and 3, or we just change this pressure loss and see what is the flow rate will be in the channel 1, and if the cooling channel 1 still can provide good cooling efficiency. Okay. The next one in our solver is the machine response. Now we have one service called machine characterizations. We can kind of like material testing, but we tested the material. We can know what is the capability of each. What is the capability of each machine, and consider what is the response time of this specific machine, and to get the better prediction of especially the pressure and also some others. For example, this is the pressure results. You can see this red line is experiment data, and once we do the measure characterization for the machines and we consider the machine response, then we can get this blue line is quite close to the real data, and it's quite important, especially for the pressure prediction. And this require a extra license too. Okay. To import, if we have this MMIP file, which is the machine file created by our service. Once we do the machine characterization, we will provide one machine file named MMIP file. And how to import it? First, we go to the process setting, switch to the machine mode. And new, click advanced, and we're able to import this MMIP file. And we can select this one for our simulations, and you can see the mark is different. This picture means this machine have been tested already. Okay, next one, our VE solver. In the past, it's quite difficult to get the jetting prediction. Now, if we consider the viscoelasticity material property, is quite easy to see the jetting. And we have two different approach. One is decouples. We still can see the jetting, but we won't able to see this this snake shape flow behavior. So if we want to see this one, we need to use the VE flow solver with a couple setting. So we have a two different setting. One is VE flow solver with decouple. The other one is VE flow solver with couples. Both of them are easy to see the jetting result, but this one is more advanced one. We could use it for the research project. Generally, I recommend to use decouple one. It's more stable, and to me, I only need to know what is I only need to know if there's a jetting problems. Not this kind of snake shape buckling result is not very important to me. Let's see, this is a real case. You can see this is a buckling result, but once I saw these jetting issues, I have to redesign either the part or more, or maybe modify the process. It's not necessary to me to see this kind of buckling result. And also with a VE flow solver, the prediction for the optical part have a better result. You can see this blue line is our experiment data, and the red line is the traditional flow solvers. It's not really fit to the real data. And the green line is done by our VE solver. And also this VE flow solver require another license. Okay, to select the VE flow solver, first we need to have a project. I will speed up a little bit. In the computation parameter setting, and we can select the viscoelastic flow. And we can decide if we want to couple the VE flow solver. And again, I recommend to use decouple one if it's general case. The calculation will be more stable. And the last one is our fiber couple solvers. The traditional way, we have a viscosity of a material, and we can calculate flow result. We have a velocity field, and then we can get the fiber orientation result. In fact, the fiber orientation will change the viscosity. And we didn't consider these kind of things in our previous versions, but now it's possible. And we can show you what is the real data. This one is a compression molding with a fiber orientation along in the direction 1. And after it be compressed, you can see this is not isotropic flow. This is an anisotropic flow. The flow from go fast in direction 2. So if we don't consider the fiber orientation will affect the viscosity, we will only get this kind of mil from result. Now it's possible when we consider the viscosity is anisotropic, we will get similar result to the reality. And also we can see the same phenomena in the injection moldings. You can see for the short fiber or long fiber, especially for long fiber, excuse me, there is an ear flow behavior due to the fiber orientation, because the orientation is different along to the edge and in the middle. If we use a decouple settings, it's very difficult to see it. But once we use the fiber couple settings, we can also see the same phenomena. Okay, how to find it? I will just directly go to computation parameter setting. Okay, first we set up the project and go to the computation parameter setting. In the advanced setting, we can find a filler parameter, and we can check this one. Consider the fiber coupling calculations. After that, the fiber orientation will affect the viscosity. Okay, that's all our new function in R17. Thank you for your time.